was like the car going towards you.
Spring system. Now, if I were to torque this a little bit. Oh!
Magic.
Magic. Okay. Now, if I were to go bigger. Ah!
And just broke the calculator.
Shock out of the way. You don't want to be doing that.
At least it wasn't your phone.
Okay? What are we doing here?
This is insane.
This all morning, no problem at all. Okay, so there it is, right there. Now, whenever you got your cell phones, other recording devices, whatever, I want you to tell me the time it takes to do 10 of those pulses as best you can. So somebody count, somebody use a stopwatch, somebody videotape it, do whatever you can. I want you to know what 10 of those things are.
Go. 1. 10. Okay, streets. 1. Hold on.
4.81 seconds.
Yeah, that's what I got too.
You got down.
In the hundredth of a second, you guys got the same answer? That's impressive. Okay, so here we go. Now I'm going to do much smaller ones. Much smaller. I want you on this. Ready? Much smaller ones.
Ready? 8, 9, 10. Matt, I thought you were doing it. Oh, I was just counting for no one.
Just go back and count it.
Do it again. Let's go. It's okay. Both of you do it. Let's go. You back up. Anyways, want everybody doing it.
Spanish is for everyone to know.
What?
Uno, dos,
4.4 both times? You got 5 that time?
Did you guys get that? Or no? Okay, Mominos.
Now, I went from going full down, up and down, to half up and down, and we got roughly the same time. Somebody said exactly the same time. Somebody said a little bit higher. Somebody said a little bit lower. What's happening here is when you have a mass spring, when I pull it farther, there's a greater force, right? Because this force depends on how far you pull it. So therefore, there's greater acceleration. Greater acceleration means greater speed. So as it turns out, if I do this right, and I have a good spring and a good mass, what happens is when I pull that thing down, I end up with the same period no matter how hard I pull it down. So I don't break the spring. Okay? That period is dependent on a whole bunch of mathematics you can't do. So we're going to simplify it a little bit. We're going to say some guy actually sat down and measured it. By the way, they did that first before they did the math. So it's just as well. The period is equal to 2 pi square root of. Now, what makes it go faster and what makes it go slower? In other words, what would make it I should have said that backwards. What makes it have a longer period? What would make it a less long period?
The length in between the coils.
The length in between the coils. Okay, what else you got? The mass. What's the mass going to make it go faster or slower?
What?
Do they make it go faster or slower? Do they make longer periods or shorter periods? Let's put a big old mass on it. What the heck? Why am I asking the question? You got a big old mass? Okay, brace yourself for impact. Get your calculator out of the way. That's a 1 kilogram mass. It's bigger than what I want.
That's going to be a longer period.
It doesn't make it off the table. All right, I got to need to get something less than that. I got 500 over there somewhere. 500. Oh, that's a 200. It's the same one. All right. No, that was a 500. No. Wait, what happened here? That was 500. That was 1,000. Wait, what should I do? I did this 200. 200. That's not helping me any. I got 100. I got less. This is 50. 50. Here we go. 50. Don't pull on my spring. Okay, here we go. 50. Ready? Oh, too fast. All right, hold on. You look crazy.
I'm ready.
Higher.
A little faster, you think?
Yes.
So the bigger the mass, the longer the period. That's what T is going to mean. So period is going to be longer. So M goes on top, and we'll put something else at the bottom. What else is going to determine the period of spring, mass spring? However you pull it, doesn't matter. Yes? The spring constant. The constant of the spring.
Okay.
How springy it is. How quickly it restores itself back. How much force it drives the thing with, right? But the stronger the spring, the faster it's going to go through the cycle, right?
Yeah.
So therefore, this is my equation for a mass spring system. Okay, that's on the formula sheet. that'd be
Literally,
fun.
P-test, can we go back to like when we first learned about spring?
Matt, we have a review session today.
So yes, during the review session, or maybe not during that, or some other time. Okay, good. So when it does this, if we were to look at a graph of, say, displacement, in this case it'd be y because it's going up and down, versus time, I started with it pulled way down, right? It would look like this. We call this, if I did it right, this is our amplitude, how much it's going up and down. And this is our period. And if you think about it, we talked about that in trig class, did we not? Okay? We talked about amplitude. So it works the same way. You can write a formula. Y equals, oh yeah, here it comes. Amplitude, sine or cosine. You've got your K times your T plus your C plus your H. Now, we're physicists. We're going to set 0 to be the middle, so that's never going to matter to us. Okay? We're going to try to avoid having starting conditions because who cares? So then you end up with this equation, which looks like this. Sine KT, we start in the same place. So this should be the formula in your formula sheet. So you find the formula in your formula sheet and tell me that I'm wrong, because I am wrong. That's not the formula they chose. Formula sheet. Nobody has a formula sheet. I've only given you like 80 of them.
Where would it be?
There's a position equals A cosine 2 pi.
Aha! Position equals
Amplitude,
amplitude,
cosine,
cosine,
2 pi,
2 pi.
frequency,
Frequency,
times time.
time. What the heck? Frequency.
Matt, where is that?
It's down the left-hand side about most of the way down. It says,
2/3 of the way down. Starts with an X.
that's what it, yeah. Okay, so if I look at this formula, I go, this makes no sense at all, Mr. Redney. Ah. Remember K was 2 pi over the period, right? Remember that? And then, and therefore, a period is equal to 2 pi over K. Agree with that? Therefore, we know what frequency. Frequency is 1 over the period, right?
Yeah.
So we did that earlier. So frequency is 1 over the period, which would be K over 2 pi. So if I put a frequency in here, okay, if I put a frequency in here, everything else cancels out with my K, and I need 2 pi to fix the thing, right? So they write it like this, probably because they've not taught trig before. So don't sweat it. You'll never know whether you went the K way or you decided to put your frequency in here. You may do it either way. By the way, your trig teacher's never going to know if on the final you use frequency instead of K. He's never going to know. Okay. K is handy when calculating phase shifts, which we're not going to worry about.
Which one are we supposed to use?
Okay, so this is the formula you're going to use. This is frequency. This is amplitude. And you're familiar with everything else. That's time, right? So that's the formula. Now, they have never once asked you to do anything useful with this. They've given it to them, well, I think twice they've seen. And they basically said, what's the amplitude? It's a number out in front. Oh, they want the actual number out in front. Sometimes it's an A, so you have to write A. Good? Okay. They will do this from time to time.
What do we write that for? Oscillation?
It'd be oscillation. Or sorry, I meant that for simple harmonic, but I don't care. But it's
Is it
simple
for
harmonic voice. Feel free. Anywhere over there. I'm going to rework this worksheet. Reason I don't want to get into. It's got to be redone this summer. Go crazy. Simple harmonic motion. So if it looks like this, it's simple harmonic motion. Now, be aware that in real life we don't do simple harmonic motion. What do we do? Complex harmonic motion, which we're actually going to call damped. Shh, listen to this because AP Central, this is one of their questions. Okay, we got to be quieter so the microphones don't hear this. Because this is one of their questions they're going to ask in one of the next 4 or 5 years, guaranteed. It's this. Damped harmonic motion. What really happens is the amplitude does what? Because the speed doesn't change, the period doesn't change, so the amplitude would get, does it get bigger? It gets smaller, right? So the amplitude gets less and less and less. So that what really happens in real life is it looks like, right? It looks like this, and then by the next time it's not quite as high. Oh, I got a choice. And then not quite as high. And it kind of, and the periods stay the same. These stay the same,
Really?
but the amplitude starts to get less and less.
How does it say the same?
Because remember, how hard you pull on it determines how fast it goes. So it turns out it doesn't matter how hard you pull on it, because the faster you pull, it gets more acceleration.
Oh.
Right? More acceleration. More acceleration means I'm going faster through my cycle than when I go a little bit and I go a little bitty up and down. Right?
Yeah.
Good? All right. Happy? Absolutely not. What? This is one formula. How hard can it be? Okay, so that's one formula, because we can't have just one formula. We want to have two formulas. Right. The land is sidetracked. Here we go. Second simple harmonic device, or allegedly so.
That's oscillation. Newton.
This does the same exact thing. If I go a little bit, it goes slower, but the amount of time it takes to go through a cycle is the same.
Are you serious?
Serious. This is why grandfather clocks. This is why grandfather clocks work. If they didn't keep the same amount of time, no matter how far out you are, grandfather clocks would have different. The clock would change its speed as it's going around, right? When you first start a grandfather clock, it's got the big swing to it, but it's going faster as time wears on. It's smaller, but it's going slower. Okay, the period stays the same. All right. So I want you to write down the period stays the same. And because I lied to you, and I want you to understand the lie, and then I'm going to fix the lie in just a moment. Yes.
This might be the dumbest question ever, but do you have to manually redo the pendulum in the grandfather clock?
Yeah, or there's actually ones which now have battery where they kick it once a day. You just kick it up and then so on. And then there's also ones where they have a key, right? The key wind. And so you got a spring in the top that slowly kind of keeps it in place. Once it gets down to a certain point, it kicks it and then moves out. And then some of those are so well balanced that they can run for 60. Once you wind it up, it's 60 years. Keep your pocket. You know, they'll just go forever because there's nothing. There's almost no friction at all in this. Okay? Now, those are the kinds you buy for hundreds of thousands of dollars, not the one that you buy at the corner store.
Sounds like a waste of money.
That's got a battery that plugs in the back. Now, there is something issue at grandfather clocks. You will see they're always narrow. They will never allow your pendulum to get all the way out here. And why not? That would last longer, wouldn't it? It makes perfect sense that I would be able to go out farther. It turns out the reason why it's simple harmonic motion is because the farther you get out, the bigger the component is in this direction, right? Which is what, if you think about it, let me draw the rope. Oh Lord. Okay. Let me draw the rope. Here's my rope. So I got a component. This is pulling up, but it's also pulling that way, right? So if I'm down here, I got a littler component that way, right? And so my force is less. Turns out it's not perfect like a spring. It's off by a little bit, and it gets worse the bigger angle you get. Okay. In fact, it gets worse by a bit you can actually measure. If you type in theta in radians, and you type it in sine theta, the difference between those two answers is the actual difference in the forces. Okay. Not a big deal. So the only thing you have to remember from this is this: if it gets over 15 degrees, that's the common agreed acceptance. It starts to become noticeable in about the 100th decimal place. Not the 100th place, right? Not the 100th decimal place. The 100th of a second is when it starts to become noticeable. Okay. You get above 15 degrees, suddenly it's off by enough you can notice it. Okay. You get to 45, it's a lot off. Okay. And that's due to the fact that it's swinging this way, even though it's being pulled that way. This is farther distance.
So if they just like on grandfather clocks, they just wind
Yes,
and then
like
it just
this,
goes
and
for
let go of
60
it,
years.
click. Well, the ones that have the springs line in the back, where you get a key and you wind them up, they got a coil in the back. And so if the thing ever gets down to a certain point, the coil just unhinges one spot and kicks the bar, and the bar pops up, and then it just keeps going. Okay? All right, I'm